Okay. Okay. All right. Okay. Good. So, it's nothing against modular arithmetic. Bye bye. And we're going to do countability and uncountability today, and some computability. Okay. Okay, so remember polynomials, this is a main fact, right? Is that a set of d plus 1 points determines a degree d polynomial. Okay? Well, we use that fact sort of powerfully for both secret sharing and erasure codes. Essentially, as soon as you see this fact and you see the definition of secret sharing or erasure codes, you're like, oh yeah, duh, right? I mean, encode a secret using a k-1 degree polynomial, and you can share it with n people. That's the whole thing. You want to share a secret so that any k people can reconstruct it, but you out of n, right? So all you do is you hand out n points on the polynomial. Okay, and this other one, encode the message using a degree n-1 polynomial that has n packets on it. It's n packets of information, and you send n plus k packets or point values, and any n is enough to recover. Okay, and this one is a little more subtle. You can recover from k corruptions. Here you actually receive all the packets, but some of them are corrupted, and you don't know which ones. Okay, and so again. What we showed using a pigeonhole argument, that there's only one polynomial that contains at least n plus k. In particular, the original one contains n plus k of the points, right? Because you've only corrupted k of them. Okay, so the original polynomial does contain n plus k. So the interesting part here is to show no other polynomial contains n plus k. And then we use this pigeonhole property, right? If you have n plus k, if you assume there's a different polynomial that contains n plus k, they must overlap on n points, which means they're the same polynomial. Okay, right? When you do these things, it's about the argument, right? We're not like, even here, way back here, why? Right? That's what you should be thinking. And you should know the argument, right? There's one argument is, why do you know you can build a degree d polynomial? That's because of Lagrange interpolation. Why do you know there's a unique one? That's because if it has a root, you can factor out a factor of x minus a. And then you do induction, right? So that's essentially all the technical content in the last week. So except this part, this magic. How do you actually recover this n plus 2k packets? How do you do it efficiently? How do you know where have my bad packets gone? Right? That's the question, right? There's some that are corrupt, and now you can try them all to just try all possibilities for the corrupt packets and fit the other pet points, but that's very slow. So what Berlekamp and Welsh, it's called the Berlekamp-Welsh or Welsh-Berlekamp, I forget which, decoding algorithm. And what they introduced is this idea of an error locator polynomial. And error locator polynomials is using the same sort of idea. It says, oh, I could write down a polynomial with k roots. Okay? And if I write down a polynomial with k roots, those k roots could be at places where the error is. So if I multiply both sides of this equation by this error locator polynomial, it is possible there does exist a polynomial that will zero out the bad equations. Okay? And that's the idea of the error locator polynomial. And then they observe further that a polynomial times a polynomial is a polynomial. Right? That's this p of x times the error polynomial is a polynomial. And now you're just reconstructing polynomials again. Okay? So it's a relationship. There's a big field. It's in coding theory. What this is a linear code. What you have is you're really taking your message, which is n packets or n numbers, and multiplying them by a matrix. That's what it looks like. And for example, the column, the coefficients, the packets are the coefficients of the polynomial, and each row of the matrix is some 1, x1 squared, x2 squared, x3 squared, and so on. Okay, and then you just do each row is a different value of xi. Okay, so it's an n plus k by n matrix. So any linear code basically works. Like if you just take a random matrix, it basically is also recoverable within with high probability. But it's, this particular matrix, this van der Waals matrix, has some efficiencies. You can solve linear systems using these in this form, 1, x squared. The particular linear systems that we see that come up are in fact easier to solve. I didn't give you more efficient algorithms, but there are more efficient algorithms. And there's all kinds of these algebraic geometric codes which work with various parameters. Okay. I mean, the big question here, the big thing here is the problem with Reed-Solomon codes is the characters are big, right? You have log p bits. So in general, for example, when you're writing stuff on a disk, you're just writing sequences of zeros and ones. So they're bit errors. So changing this, a lot of the action in coding theory is how do you deal with bit errors from long strings of bits, okay? And it's a much more complicated process, and when you don't have this nice field to work with. But that's, so tons and tons of work on this, okay? Okay, so modular arithmetic, modular prime, you can add, subtract. It's multiplication and addition is commutative and associative. You have inverses. You have multiplicative inverses. You have both additive and multiplicative inverses. It allows for solving linear systems, and we can do this polynomial interpolation using this modular arithmetic. Okay, we could just work over numbers mod p. Okay, why don't we always use modular arithmetic? It seems so awesome. Okay, 4 is greater than 3. That seems fine, right? That's the sort of, what do we use numbers for? Well, we compare things, right? That's true. Is 4 greater than 3 mod 7? What does that even mean? Yes? Maybe? Well, 4 is also negative 3 mod 7. So is negative 3 greater than 3 mod 7? Right? Okay, so there's something weird about modular arithmetic, right? These numbers don't have an ordering. Right? They simply don't have an ordering. It doesn't make sense to talk about order. And we like order with our numbers, right? There's other problems. 4 is kind of close to 3, but you can't get any closer. This is a problem with the integers as well. But can you get closer? Sure. You do 3.5, and you can get closer, 3.25. And you get closer, 3.1, and 3.001. What am I talking about? I'm talking about calculus. I'm talking about a limit. You can get closer and closer to 3, right? Does that make sense? Nobody should understand that I was talking about a limit, but okay. But that's what I am talking about. There's this notion of a limit, right? Remember all that stuff we did in high school and derivative and calculus? Yeah, you need something fancier than modular arithmetic. There is no for modular arithmetic. There's no such analog. Okay, no calculus at all, right? So it really isn't a complete system, it doesn't replace what we work with. Okay, sad face. Okay. So now the next question is how big is infinity? Okay, so what does it mean? It's obviously just infinite, right? It's big, right? It's infinite. Okay, so. In particular, let's make this a little bit more concrete and say how big are the reals and the integers? Well, they're infinite. Their size is infinite. Is one bigger or smaller? Yeah, okay, we could both agree but are they the same sort of infinite? Is one bigger or smaller? Okay, so first question is how do you even tell if two things are the same size, right? So one way you could do, are there the same number of squares and the same number of circles up there? Yes. Okay, why? Well, okay, so it's like, do I have the same number of fingers on this hand as I do on this hand? Yeah, because you know what? I don't know. Yeah, I do, right? They're the same number. Does that make sense? Because I made a bijection between my fingers. Okay? I didn't count them. Right? It's hard to count infinity. Right? So you have to sort of think about what is another way to say things are the same size. Right? How do we tell? So one way to say it is you make a function of circles to squares, and this is, we'll draw the, here it's clear what the bijection should be. We just match the colors, right? The red square to the blue square, red circle to the red square, and so on. Okay, and it's 1 to 1. Now each circle is mapped to a different square. This is what 1 to 1 means for all x and y in the domain. If x is not equal to y, f of x is not equal to f of y. Okay, and it's onto, each square is mapped to from some circle. Means for everybody in this range, there exists a preimage, C, in the domain such that S is equal to f of C. Right? You've seen this definition a lot of times, but let's just see it again. If there's a function from the domain to the range, to this, from the set D to this set R, that's 1 to 1 and onto, then their sizes are the same. Okay, we've already used this a lot of times. Okay, given a function f of d to r, it's 1 to 1 if this is the case, or this is just a contrapositive of that statement. If for all x and y, if x is not equal to y, then f of x is not equal to f of y. The contrapositive of that is if f of x is equal to f of y, that implies x equals y. Okay, and so on. Okay, this is for every element of R, there should be an x that f of x is equal to that element, which is y. Okay? And this is what we sort of said on the previous slide. So this is our definition of countability, right? This last thing, we're saying that the size of D is equal to the size of R, if there's a bijection. Okay? Okay, so this all makes some sense already, so now I don't need to say the number of fingers I have is 5. I could just say, okay, whatever number I have, I don't know what number I have, I know they're the same. Okay? Does that make sense? Okay. Okay, so now how to count. Okay. This is 0, 1, 2, 3. These are kind of called the counting numbers, right? Because you count with them, right? So they're also the natural numbers. So now when we say something is countable, it means it has, if it's countable at all, if there's a bijection between the set S and some subset of N. Okay, that's just what it means to be countable. You have a bijection between your set, then my fingers is countable, because for each finger I can assign this guy 0, assign this guy 1, assign this guy 2, assign this guy 3, and this one 4. Therefore, the number of fingers is countable. Right? Now, if it's finite like that, if the subset is a finite subset, then it has finite cardinality. In this case, the cardinality is 5. If the subset of N is infinite, S is called countably infinite. Okay? These are just terminology we're going to use. Okay? Okay, so which is bigger? The positive integers or the natural numbers? Well, the natural numbers have all of these. The positive integers have that. So which one is bigger? Now, they both have infinite size. Yeah. 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 So they have both positive size. They both have infinite size, right? So you could just say same. But that's not what right? Because they're both infinite. On the other hand, you see that one has an element, one is a superset of the other one. So it's a little odd to say they're the same size, right? One guy has an element that the other one doesn't have. So it must be bigger, right? If I had more fingers on one hand, then that would be more fingers, right? Okay, so where's 0? So, they're both infinite, so there must be more natural numbers, which is, but again, it's hard to say how big these things are because they're infinite, right? So what we're going to use this other definition in terms of comparing the sizes of these two sets. Okay? We're going to consider a bijection, f of z, and f of z is equal to z minus 1. Okay, so is it a bijection? For any z1 not equal to z2, you know that z1 minus 1 is not equal to z2 minus 1. Okay? So that's the definition of bijection. If x is not equal to y, then f of x, which in this case is z1 minus 1, is not equal to f of y, in this case is f z2 minus 1. Okay, so it's 1 to 1, and for any natural number n, for z equals n plus 1, f of z is equal to n. So every natural number is the image of some pre-image of this function. Okay? So it is a bijection. So that says they're the same size. But where's 0? Well, it comes from 1, right? That's what this is saying. Right? The bijection says we are actually matching them up, right? So the 0 in the natural numbers comes from 1. Okay, but then where's 1? Well, that comes from 2. And then where's 2? That comes from 3, right? And eventually, since this goes on forever, you never lose anybody, right? Everybody's there as an image. Okay? It's this foreverness that says, well, this doesn't end, right? It just goes forever, right? There's no natural number that does not have a pre-image. All right? Okay, so a bijection, notice that, there's a bijection between n and z plus as well. What we did is we mapped from z plus to n, but this, in this case, there was this other bijection. We could have mapped from n, the natural numbers, to z plus. Okay? So 0 to 1, 1 to 2, we could have gone the other way. In fact, this is not just the case for this particular example. It's always true, right? If we had this bijection this way, from the circles to the squares, we just reverse the arrows, and you get a bijection from the squares to the circles. Okay? So the inverse function is they always have an inverse function, and the inverse function also is bijection. Okay? So now you can prove countable either way. You can prove that two things have the same size either way by taking a bijection from one to this one or from this one to that one. It doesn't matter. Okay? For the integers as well. If you want to prove something is countable, you can actually just take a bijection. What we said the definition is bijection to or from the natural numbers implies countably infinite. So either way, whatever is more convenient. Okay? So that's we're going to use. This one, we're going to use a bijection from the natural numbers to the even numbers. And this one is clear. What's the bijection we're going to use? Yeah. Right. Right? Does everybody see the bijection from the natural numbers to the even natural numbers? Yeah, you just multiply by 2, right? And then you get an even natural number. Okay, it's on 2. Every even natural number has a f of e over 2 is equal to e, right? So for all e in the natural numbers, I just calculated the pre-image, which is e over 2. Okay? And e over 2 is natural since e is even. And it's 1 to 1. For all x and y, if x is not equal to y, 2x is not equal to 2y. These are just what we know from arithmetic. Okay? So f of x is not equal to f of y. So evens are countably infinite. Evens are the same size as all natural numbers, right? It's really wild, this countability, right? You think there's got to be fewer evens than there are natural numbers, but in this setting, they're both infinite, and so they're both the same size. Okay? Is it mind-blowing at all? Who thinks it's mind-blowing? Yeah, I think it's a little mind-blowing, yeah. Okay. Okay, so what about integers? Well, yeah, I can draw another bijection here, right? If I'm gonna give a bijection from the natural numbers to the integers. So for each natural number, what I'm going to take it, if it's even, I'm going to take n over 2. If it's even, n over 2 will be an integer, right? It'll be a positive integer. If it's odd, if n is odd, I'll take a negative, right? I'll take this weird negative. But n plus 1 will be even, over 2 is an integer, and you take the negative. That's gonna hit my negative natural numbers. Negative integers. Okay. Okay. So so now what we want to say is for 1 to 1, if x is not equal to y, then f of x should not equal f of y. Okay, if x is even and y is odd, well, f of x is non-negative and f of y is negative. So therefore, their images are not the same. F of x is not equal to f of y. If x is even and y is even, then x over 2 is not equal to y over 2, right? Because if they're not equal to each other, dividing by 2 doesn't make them equal, and so on. The last case is odd and odd, and you can figure it out. Okay? Okay, so for any z in z, you want to say it has a preimage, right? It's onto the integers. Okay, so if z is greater than or equal to 0, f of 2z equals z. That's just what we're doing up here, right? And 2z is a natural number, so it is a natural number, and it is mapped to this number. If z is less than or equal to 0, if you plug in 2 times the absolute value of z minus 1 into this function, you'd add 1, and then you get 2 times the absolute value of z, and then you divide by 2, and you get the absolute value of z, and then you negate it, right? And then that would be z, negative, that would be z. Okay, negative the absolute value of z is z if z is negative. Okay, and clearly 2 times the absolute value of z plus 1 if z is an integer is a natural number. Okay, so it is in the domain. So this says integers and naturals have the same size. Now this is annoying. This starts to get annoying here, okay, to write these in and do these proofs. So let's think of another way to do this, right? Let's just think about, I guess math guys like f of x and not equal to y. Oh my God. I'm kind of a math guy, but not, fake math guy. But for me, I'm more of a computer person, right? So here, I just want to say, well, let me just list the integers, right? So I could do this. I can say, look, I can think of this as a listing, right? The first element of the list is just the image of n, right? The image of 0. The next element of the list is the image of 1. I'm just writing down this function as a big table, okay? So in fact, what is a listing? Well, a listing is a bijection to the natural numbers, right? It always is. Any listing, you can just say the first guy in the list maps to 0. The second guy on the list maps to 1. The third guy on the list maps to 2. So if you have a way to list all the elements of your object, then you actually have produced a bijection to the natural numbers, right? Does that make sense? So the thing you have to prove is that the function that maps you to the natural numbers, or maps from the natural numbers to this set, is just the position in the list. That's it. Okay? So if it's finite, the bijection is with some it's just the size of your list. If it's infinite, it's a bijection with all the natural numbers, right? If this listing is infinite. Okay? So but now, so the problem becomes, instead of one of designing this function, it's almost designing a procedure to write down all the elements of your, if you want to show something is countable, just describe a procedure that tells you how to generate a list of all your items, where every item is in a fixed finite position. Okay? Does that make sense? Okay. And I'm going to use this word fixed. Every element is in a fixed finite position. That means every element is mapped to by some single natural number, right? It's somewhere in this list. And if you tell me the element, I could tell you it's here, or it's approximately here, or it's before here, right? So I will use that a few times. So if I say, I don't know, any element that looks like this is before this space, is it in a fixed finite position? Before space 100? If I say this element of this set is before position 100, is it in a fixed finite position? Yeah, it's in either 0, 1, 2, 3. Oh, it's in one of those positions. Any one of those is finite, right? If it's listed once in the list and it's in one of the positions. Okay? Let me get to it again. So that makes it complicated, but let me get it back to simple. So enumerating a set implies that it's countable. When we say enumerating, it's a fancy word for listing, right? We enumerate them. You output an element of S, you output the next element, any element of X. Any element of X of the S has to have a specific finite position in the list. Just one position. So 0, 1, minus 1, 2, minus 2, right? This is the listing we saw before. And we can just continue this pattern and you know you're going to get to everything, right? Because it's a procedure and you know you just increment 2 to 3 and you write down 3 and negative 3. If you think about K, you know it'll be in position 2K roughly, right? Okay, so another way to list it is we could have listed all the positive numbers and then all the negative numbers. Is there a problem with this? Yeah. Right. Right. It's not even well defined when negative 1 comes. When does negative 1 come? Well, it never comes. Or what? What does it even mean to list an infinite set and then another infinite set? Right? So this is not a valid listing. Right? The second, we did a valid listing there, but this one, you never get to negative 1. It doesn't appear in a specific fixed finite place, right? Right? At infinity, that's not a fixed finite. That's exactly the definition of not finite, right? Okay? So you need to be careful when you do this, right? It doesn't forgive you from writing anything you want, right? You have to actually do it in a reasonable fashion. And you've done this before. Who remembers doing this before? Do you remember streams? Who remembers streams? Okay. Do you remember interleaving streams? Right? Streams are infinite objects. You can keep pulling from all of them. If you want to combine streams, you don't pull forever from one and then start on the other one, right? What do? You pick one from each stream. Right? Streams, right? This is like streams, right? This is a stream. It's a stream of the positive numbers. This is a stream of the negatives. So if you want to list, the only reasonable way to sort of handle both of these lists is take one from one, and then one from the other, and then one from one, and then one from the other, right? Okay, it makes no sense to just go through the whole pile of an infinite set. Okay? So enumerating a set implies countable. Any subset T of a countable set is countable. There's another corollary. This is kind of almost obvious. You just enumerate T as follows. You get next element of X, right? What is enumeration? It says, enumeration is essentially a listing, or it's a program that gives you the next one, or some sort of action that gives you the next guy. So each element, you tell me the next one. Okay, I got it. Tell me the next one. And now this one, I only output it if it's in T. So for any subset of S, it must be countable because I just take the countable procedure I have for S, because I'm assuming S is countable, and then I just only output the subset that belongs to T. It also amounts to the same thing as writing down the listing of S and crossing out the elements that aren't in T. Okay, so Z plus is countable, the positive integers is countable. It is infinite since the list goes on forever. So there's a bijection with the natural numbers. So it's countably infinite. That's what we mean by countably infinite. So all countably infinite sets have the same cardinality. They have the same cardinality as the integers. Okay? This is what we mean by cardinality of infinities. Okay, so here's another enumeration example. It's like here's the binary strings. So here the binary strings are 0, 1 of any length, including the empty string. So you start with the empty string, and now I start with the then I do 0 and 1, and then I do 0, 0, 0, 1, 1, 0, and 1, 1, right? And so on. So in this enumeration, it seems like it's trivial, but I'm doing something a little bit carefully here, right? Because I could have done Well, here let me argue that every string does appear in this enumeration. So this enumeration, what it does is it enumerates all the strings of length 0. That's the empty string. Then it enumerates all the strings of length 1, which is 0 and 1. And then it enumerates all the strings of length 2, and so on. And all the strings of length 3. Okay? So now I'm not going to be very precise about which string it is and where it is. I don't really care particularly. I just need to know that this kind of procedure will output the string at some place that's a finite and specific. There's a finite place that will output it. There's only one place that will output it. So if for any string it appears at some position in the list. Now the way I argue that is any string has some number of bits. You could look at the string and you could say, oh, this string has 10 bits. Okay? So now I think about my procedure and I say, well, this procedure will list it before the position 2 to the 10 plus 1. Okay? Because that's how many strings there are with fewer than 10 bits. Okay? So that's the argument. So it becomes it becomes an argument instead of like, oh, f of x is this, f of x is that. It's just like, here's a procedure, here's an argument that I will output every string. Every string will be output at a specific finite position. Okay? Okay, you should be careful again here, right? I could have done it this way. I could have listed the strings as the empty string, and then, just because I like zeros better, I'll start with 1 0, and then 2 zeros, and then 3 zeros, and so on. But you see the problem with enumerating it this way, right? You see the problem? You never get to 1 again. Right? It's disaster, right? Okay? So that you need to really interleave. You need to really think about how you enumerate to get it right. Yeah?
So for your argument, when do you prove that the bit string with 2 to the n plus 1, how do you argue that that's also finite?
Bit string with 2 to the n plus 1.
Basically, you're arguing that the n bit string will happen before the 2 to the n plus 1 bit string, but you're assuming that that occurs at a finite position.
I'm just what I'm saying is that here's the argument, okay? All the strings of length 1 will appear before position 3 because there's 3 strings of length 1 or less, right? So if it has 1 bit or fewer, I know it'll appear somewhere in the first 3 positions, okay? If it has 2 bits or fewer, I know it appears in the first 2 to the n, 2 to the 2 plus 1, 2 to the 3 positions. And that's because I know how many strings there are with that many bits in it. Okay? So I don't know, like I didn't say, like for 0000001, I didn't really care much about the order there. So I didn't really fully specify the bijection. But whatever order it is, whatever your program does, it has to output all of them before it outputs a longer string. Okay? So if it has n bits, I know it's somewhere in this first set of whatever number of positions. Okay? I just want to avoid having these like little trivial calculations as though it has to appear exactly in this position. Right? Okay. So let's enumerate the rational number. So at some point we're going to have a listing, okay, from 0, and then there'll be a bunch of rational numbers, and then there'll be 1/2, and so on. Okay? So 1/2 should appear in a specific finite position, right? So let's just try to list them in order. So we know before 1/2, 1/3 must be before 1/2, right? Does that make sense? Because 1/3 is smaller than 1/2. And 1/4 must be before 1/3. And 1/5 must be before 1/4. And 1/6 must be before. So that says the number of rational numbers before 1/2 is infinite. Right? Does that make sense? So that's a problem. Right? If you list any 2 fractions, it's even worse. Any 2 fractions has another fraction between it. So I can't even list a pair of fractions next to each other. Because whatever you list next to each other, I could say, wait, there's another fraction that's in between it. Like just take the average, right? That's annoying, right? Okay. So it says, basically it says maybe you can do a listing of the rational numbers, but you can't do them in the order you think you should do them in, right? You can't do them in the order of what their value means to you, right? Because the value, 1/3 means something to you. It means a rational number whose value is 1/3, and that value is less than 1/2, so intuitively 1/3 should be listed before 1/2, and 1/4 should be listed before 1/3. But that's not what countability says. It says any ordering of the rational numbers, right? You could write down a list where you get to every rational number at some point. Okay? So what we're going to do, instead of thinking about rational numbers, we're going to think of pairs of natural numbers, right? Obviously, the pairs are going to correspond to the numerator and the denominator at some point. But right now, just think of pairs of natural numbers. So 1, 2, 130. This notation, n cross n, means you take an element from the first set and an element from the second set. You make this tuple, right? That looks like that. 1, 2, or 130, and so on. Okay, so finite sets, then what's the size of S1 cross S2? If S1 and S2 are finite in size. Yeah. Not quite. Yeah. Yeah. Right. Right. It's that. Does that make sense? So you just say, well, how many possible pairs that look like this? Well, there's the size of S1 possibilities here times the size of S2 possibilities here. So there's a S1, size of S1 times size of S2 different possibilities. Okay? So now we know that, but yeah, so this would tell us that, what does that even mean? So if you sort of generalize to countably infinite, right, this size is clearly not always the same as the size of S1 or the size of S2. You would expect it to be larger, and typically it's sort of the square, right? You would get the square. What does the infinity squared mean? I don't know. I don't know what infinity squared means. It actually has no meaning. It's still just infinite, right? So, right, it's already a little bit, you would expect this to be of different size, n cross, and again, just like we've seen many times, our intuition is not perfect for infinity, the reasoning about infinity. Okay, but I'm going to show you that it is actually countably infinite. There is a bijection to the integers. Okay, so and again, we're going to enumerate in a list. So 0, 0, 1, 0, 0, 1, 2, 0, 1, 1, 0, 2. Now, if you look at let's just look at the list up there. What is 0 plus 0? That's not a hard question, right? It's, okay. Okay, now let's look at the next two elements. One is 1 plus 0 and one's 0 plus 1. What do they both add up to? What about the next three elements? What do they all three add up to? 2. So that's how I'm listing them. I'm taking all the ones that add up to 0, the pairs that add up to 0, which would be this grid point. Okay, and then I take all the pairs that add up to 1, which is this is essentially, what is this point? It's 0, 1, and this one is 1, 0. Okay? And then I take all the ones that add up to 2, which is, this is 0, 2, 1, 1, which one is first? Oh, this is 2, 0, 1, 1, 0, 2. Right? If you take the x and y axis. Yeah. Okay, so then we're going to list it in this order. All we're doing is taking these diagonals. And each diagonal has a property that each of the grid points, if you add up the x and y values, they're equal to some constant. Right? It's a line of slope -1. Okay? Yeah.
What about cases where 0 is the denominator with those rational numbers?
Well, we're not doing rational numbers yet.
Oh,
Just doing pairs of integers. Yeah. But we will do natural numbers. Okay. But anyway, so you can continue, right? And so now I want to say every one of these grid points. Essentially, we're counting these grid. We're showing these grid points. We're talking about the size of these grid points. We say the pair AB, which is one of these grid points, it's over by A and up by B, is in this first some number of elements, right? You just look at the triangle and you see how many things are below that line. Okay, and you say, well, it's going to be one of those points. Okay, so it's just it's sort of the area of this triangle, roughly. I know I'm going to be there, right? Okay, so then it says what I've done is I've listed all the pairs A, B, where A comes in the natural numbers and B comes in the natural number in some order. That means where every pair appears in a specific finite place. So that means that the cardinality of this is the same size as the natural numbers, which is odd. This is weird. It's not odd as in odd. It's odd as in strange. Okay. So, okay. So what about now? We want to do rational numbers, so we can enumerate the rational numbers. So we can just think about writing each rational number in lowest terms, A over B. Okay? That's how we're going to represent. For each rational number, we can have A over B. So if A and B are an N, with the GCD of A and B is, oh yeah, look, modular arithmetic, oh no. Okay, but that's fine. We can do that. We're good at that's fine. So now it's just an infinite subset of N cross N. And we said before, any subset of a countably infinite set that's also infinite is also countably infinite. Okay, so we know that the rationals are also countably infinite. So now these are only the positive rational numbers, so you have the negative rationals are countable by the same argument. And in some sense they're the same size as the positive rational numbers. So you can put all the rational numbers in a list by first putting all the negative rational numbers and then putting all the positive rational numbers. Yeah, no. Right? What do you have to do again? Yeah, you just say, well, I have two lists. I have the positive rational numbers and negative rational numbers, and they're a countably infinite set, both of them. And now I can take the first one from one, the second one from that one, the second one, and I have to interleave them. So this is interleaving streams again. Okay, so there's these techniques to prove to prove countability. You just have to do a bijection to the integers, which for us is just a procedure to write down all the elements of your set in some order where they all come out. Okay? This is not a procedure that writes down all the elements of these two sets in some specific way. This is a bad way to do it. It doesn't work. Okay? You really have to do this sort of notion of interleaving. But you can do that. So that's the other idea. So listing, and then now if you have two of them, you can interleave them. Or two or more, you can interleave them.
So the argument is that you can count all pairs of natural numbers, and then the set of rational numbers is a bijection to the pairs of natural numbers?
It's a subset.
It's a subset. Okay.
Yeah.
And we know
There's a bijection to a subset of the natural numbers. Pairs. Right? It's all pairs of the natural numbers where you have this condition. So then it becomes a subset of the natural numbers, right? So that condition defines a subset. Okay? Okay, good. So then, now finally, are the real numbers the same size as the rational numbers? That's the question, right? And we know the answer, because, or do we know the answer? Who thinks they're the same size? They're infinite, right? They're both infinite, right? They must be. Everything else is the same size as the natural numbers, right? I'm trying to convince you of the wrong answer. But now, who thinks they're different sizes? Yeah, okay, so they're different sizes, okay? Are the set of real numbers countable? That's the question, right? So let's just consider some of the real numbers, all the real numbers between 0 and 1. Okay? You want a break, or should I do this proof and then have a break? You want a break? Okay. Yeah. Okay. Yeah. So I had soldier surgery a couple of years ago, This is your break. You can leave. Okay. Actually, 4 or 5 years ago. So then I went to this. This is a long story. I'm like an old man. Old men have a certain property, or old people in general. When we tell stories, they're long and generally pointless. But what they're trying to do is shed experience so you understand maybe more about life at the end than at the beginning. So then what happens, I went to get surgery on my shoulder. It's a rotator cuff. So I went into the hospital, the surgery center, and the nurse came in. Oh, okay. Okay, so then somebody comes in and they said, "Oh, what shoulder? This anesthesiologist is coming in. This person's going to come in. The surgeon's going to come in. They're going to tell you what they do. But which shoulder?" And I said, "Right shoulder." And so then the next person comes in. They said, there was an anesthesiologist. They said, "You're going to have a block. They're going to give you one of these blocks, these anesthesia, which will make this nerve go dead, and you won't feel anything for like 24 hours. And then we're going to give you this thing, and you'll go out. And then the surgeon will do all this stuff to you, but he's going to come in and tell you." And so then the surgeon comes in, and he says, "Oh, okay." And then he says, "Which shoulder?" And I said, "Right shoulder." So I told the anesthesiologist, "Right shoulder." And so then the surgeon comes in, and he says, "Oh, I come and go in here. I'm going to rip your muscle off, and I'm going to cut it, and I'm going to sew it to your bone." And I was like, "Oh, that doesn't sound good." And then he says, "I'm going to scrape away the bone in this corridor this is a complicated joint. Lots of muscles sort of do a lot of things to come together. So one goes through this hole, which is tight, so he had to scrape away bones." And so he told me that, and then he said, which shoulder?" And I said, "Right shoulder." And then he says, "Okay," so then the nurse comes in, and they take me over there, and they're walking me over to the place where I'm going to get surgery. And then they said, the person walking me over said, "Which shoulder?" I said, "Right shoulder." And then I lie down on the thing, and obviously it's all set up for the right shoulder. And the surgeon wrote the star on my right shoulder, right? And so then the surgeon. Then they lay you down. Which shoulder? Right shoulder. Okay. So, and then it's like this, the anesthesiologist gives us 99, 98, 97, 96. I'm out. I didn't reach 90. Right? These people are good. Anesthesiologists are good. Really good. They were not. I had surgery when I was young. They were not so good. Now they're very good. So. Yeah, so anyway, the next thing I know, literally the next thing I know, I'm like waking up a little bit out of it. I'm in the recovery room, and I see the doctor, the surgeon, and a nurse, a male nurse and a female nurse, and the OR nurse. They're walking toward me, and I say something. I'm a little groggy. I don't know what I said. They had this look on their face, and then they came up and said, "Oh, the surgery went really well. We reamed out those things. I got all those bone spurs." I was like, "Oh, okay. Great." And so that was fine. So then I got taken home, and the next day I'm home, in bed, and the guy calls me up and says, the surgeon calls me and says, "How you feeling? How's the pain?" I was like, "I don't know. I guess there's a block there, so I don't really feel much." And he's like, "Well, did you have a fever?" Because the thing about surgeons is they don't want patients to die. And the notion of a fever is I'd have an infection, and an infection after surgery is sure death, right? So it's bad. You need to go in. So I said, no, I'm fine. And then he said, "Oh, good." He didn't really care about the pain. He cared about the fever, right? If I'm in pain, that's okay. But fever, death is bad on your record. So then he said, "Do you remember what you said in the OR when you were coming out of it?" I was like, "No." "You don't remember at all?" I was like, "I don't know. I think I might have tried to tell a joke, but you didn't think it was funny." It's very much like class. But and then he said, "Well, you looked at your shoulder and you said, 'Wrong shoulder.'" All right, so okay, so
One of the best jokes I ever told, and I don't remember telling it. I don't know. But I did say, now I see why you didn't think it was funny. And he's like, no, we didn't think it was funny, but now I think it's funny. So, anyway, it's also a joke you would never tell if you were actually conscious, because it's just too mean, right? Isn't it mean? It's kind of mean, yeah. Anyway, okay, each reel, let's think about whether the set of reels are countable. Now you should listen. Okay, so let's consider the reels 0 to 1. Each reel has a decimal representation, right? Like 0.5. It has this 0.5, and then I'm writing it differently than 0.5, right? How might you write it? Well, how might I write it if I wasn't doing this lecture? I would write it as 0.5. But I claim the representation as 0.5 followed by an infinite string of zeros. That's also a representation of 0.5. Does that make sense? That's what it is. Our representation of 0.5 as a decimal is 0.5 with an infinite sequence of zeros. Okay? Does that make sense? Now this one may make more sense. We're sort of happier with the pi having being an infinite string, but 0.5 is also an infinite string. Just anywhere in it is just zero. It's not a very interesting infinite string, but it's an infinite string. And so on. You can do 1 over e, and 1 minus 1 over e. I don't know why I'm doing all these numbers, but they're kind of interesting, I guess. There's some real number, right? It's some number. Okay, so now the point is, if I want to show that these things are not countable, so what I'm going to do is do a proof by contradiction. Okay, so I'm going to assume they are countable. Okay, so if they're countable, there is a listing. L contains all the reals. Okay, it looks like that, right? The 0th one might look like 0.5 in all zeros. The second one, the first number 1 might be this one, and so on. So it looks like that. So I'm going to construct a number that's not on this list. Okay? And if I construct a real number that's not on this list, does this list contain all the real numbers? No. Okay? So that's what I'm going to do next. I'm going to show you a real number that's definitely not on this list. I'm going to use this list to construct that number. Okay? Because I get to assume there's a list. If, it's by contradiction. I'm assuming there's a listing. And now I'm going to use this listing to construct a number that's not in this listing. Okay? So I'm going to say the first one, look, what's that first digit? It's 5. So I'm going to make this 7. What's the next digit? It's 8. I'm going to make this one 7. Oh, the next digit is 7. I'm going to make this 6. And so on. So the diagonal number here, the algorithm I'm using, it's an algorithm. I just ran the algorithm here on this list. And the algorithm is the following. Digit I is 7 if the number I on the list, right? The number I on the list is a well-defined object. I could look at the ith number on the list, and then I look at the ith digit, and then I would, if it's 7, then I write something else, 6. If it's not 7, I write 7. Okay? So now the diagonal number for a list differs from every number on the list, right? Because assume it's in position I. Oh, no, but it differs from that number that's at position I in bit I, in decimal I. Okay? So the diagonal number is not on the list, right? That's by construction, right? It can't be anywhere in the list because wherever it is, it differs from that number in position I. If it's in position K, it differs from the number at bit K or digit K. Yeah. You're assuming there's a list. Right? At the beginning, I say I have a list of numbers. Yeah. If it's countable, there's some lists. Okay? It's a proof by contradiction, right? So, but if it's countable, there is a list. Okay? And that's how I get the list. And then I just look at the number. Then if I have a list, I can look up a number in each position. And if I have a number, for a real number, I can look up the value of any finite position bit of that real number. And then I can change that value. So I'm not doing it as a procedure because this is infinite, but I'm doing it as a definition. Okay, and a diagonal number is real. It's just a sequence of digits. That's what a real number is. Okay? So that's a contradiction. Yeah. Okay, where is it in the list? Somewhere. What? Somewhere. Where is it in the list? Somewhere. So let's say it's at position K. Okay? So now I'm assuming it's at position K. Now tell me why it's not at position K. No. There's the construction. There's a construction. Look at the construction. Why is it not at position K? What does the construction say? I say, my diagonal number, it looks at position K, and it says, I'm going to make myself different from the number at position K. Or let's even call it I, right? So it's not at position K because its kth digit differs from the number at position K. Okay? So you got to go through the steps. Can it be at position? If the real number is in the list, it has to be at some position. But the way I've defined this number is it can't be at that position. Okay? I made myself different from every number on the list. Okay? Okay, good. Okay, so good. So that says this is a contradiction. It's not on the list. There is no such listing. The only thing I assumed here, the only problem, the only thing I didn't do concretely and make a complete argument is if this list contains all reals. And so that must be wrong. Okay, so set 0 to 1 is not countable. What about all reals? No, any subset of a countable set is countable, right? So if all reals were countable, clearly 0 to 1 would be countable, right? If reals are countable, then so is 0 to 1. All right, that's what it says. Okay? Assume that a set, so diagonalization, what's it look like? So assume that a set S can be enumerated. Consider an arbitrary list of all the elements of S. Use a diagonal from the list to construct a new element. That's what we did. This is the diagonal. Okay, show that T is different. This new element T is different from all the elements in the list. That's what the diagonal is being used for. Like in the real number case, the diagonal was for each for the ith element, I make sure I'm different from the ith guy in the ith digit. Okay? Show that T is different from all elements. That's this argument here that we just made, and I made me and the student made together. So T is not in the list. And now we need to show that T is in S, in the set of elements we're trying to count. In this case, T was a real number because it's just a sequence of digits. An infinite sequence of digits. And so that's a contradiction. So there can't be a list. Okay, so let's look at this one. The set of all subsets of the natural numbers. Okay, I'm going to say that's uncountable. So what's a subset of the natural numbers? 0 is a subset. 0 through 7 is a subset. Evens, the even numbers are a subset. The odds are a subset. The primes are a subset, and so on. So now I'm taking any subset. Now, let's assume it's countable. So there's a listing. I'm just going to give you the frame for the diagonalization argument with this particular set of objects. It contains all subsets of n. So now we're going to define a diagonal subset D. So we assume, again, we have a listing. So that means for each set on the list, it has a position I in the list. Right? Does that make sense? There's the listing L for each set in this, take the ith set in this list. Okay? I'm going to define a set D, and now look at this ith set. If it contains I, if it does not contain I, I'm going to put I in D. Okay? Otherwise, if the ith set does contain I, I'm not going to put I in D. So D is a subset of the integers. So for each integer, I could decide whether to put it in it or not. Okay? That's the idea. Okay? So D is different from the ith set in L for every I. This is the same argument again. Because that's by construction. I'm defining D with respect to the list. I'm using the list to define the subset of the integers. Okay? So D is not in the listing, right? Because if D was in the listing, it would be at some position I. But if it was in position I, whatever set in that position, if it might contain I, but then D would not contain I. Otherwise, if it does not contain I, it's just switched, right? They differ on whether or not they contain I. Okay? So D is a subset of n. It really is clearly a subset of n. I'm just defining a subset of the integers. For each integer, I'm deciding whether to put it in or not put it in. So it is a subset of the integers. And it's not on the list, so this list does not contain all subsets of n. So that's the contradiction. So this is another proof of diagonalization in the same frame. Okay? The set of all subsets of n is not countable. Okay? It's also called the power set. If somebody says a power set, it just means all subsets. Okay, so now let's do this, let's prove it one more time. Let's prove that natural numbers do not have a listing, which is ridiculous, right? Okay? So what I'm going to say, I'm going to try to do a contradiction proof that says natural numbers are not countable, which is our definition of countable, and show you where I'm using what. Okay? So you make a diagonal number D, you say you differ from the ith element of L in the ith digit. That's what you're going to do. Okay? It differs from all elements in the listing. This object that I built does differ from all elements in the listing. Right? And D is a natural number. Okay? What's wrong with this proof? Yeah. No, it's not a natural number. Right? Why not? Because D, any natural number has a finite length. You tell me a natural number, I could ask you the number of digits. That's not true for reals, right? Reals have this infinite representation. Okay? We know lots of reals that have need an infinite representation, right? So whereas natural numbers all have a finite number of digits. So you can't build this natural number. This object you built is this infinite sequence of digits, which is not a natural number. Yeah. No, the proof is the object I'm constructing, it doesn't have a finite number of digits. But here you can always say leading zeros. You could add leading zeros for no reason, right? But, adding leading zeros really doesn't mean anything, right? In the end, a natural number you could add as many leading zeros as you want, but there's a substring that contains all the things that aren't leading zeros, right? So this last thing, it never stops, right? It has to have an infinite sequence of digits. Okay, so this is a fake proof, right? It's where it doesn't work, and it shouldn't work because the natural numbers are countable. Okay? Okay, so now we're going to prove there's no set with cardinality between the naturals and the reals. That those cardinalities are really, we're not going to prove that. That's really hard. We can't do that. This is a really hard problem. It's so hard that it can't be done. Okay, so now let's think about cardinalities of these. But that now we have to talk about the cardinalities of uncountable sets. This hypothesis, yeah.
Can you go back to the subset proof where you said the power set was uncountable? Because that's not infinitely. Each subset is not.
Yeah, each subset of the natural numbers is, for every natural number, you have to decide whether it's in it or not. So it's infinite. Okay, so so now what this problem is saying, how do you compare cardinalities between uncountable sets? So here you go back to your bijection. Is the cardinality of these real numbers, of this interval, smaller than the reals? And the answer is no. You can write a bijection. Now here you can't do a listing. There's no way to list the reals. So to compare the reals between 0 and 1 and all the, say, positive reals, you have to do a bijection again. Okay? So, because there's no listing of the reals. Okay? So it's 1 to 1. So this function happens to do it. What we're doing is, for all the real numbers, if they're between 0 and 1, this case basically says, if they're between 0 and 1/2, you shift it into the second half. You just shift 0 and 1/2, that interval, to 1/2 0. That's what you're doing here. And that's a bijection. And the second thing, what it does is for all the numbers greater than 1/2, it puts them in the interval from 0 to 1/2. Okay? So if x is not in y, if both are in 0 to 1/2, you're just shifting. So their images are not the same. If neither are in 0 or 1/2, it's a division, right? You're taking this reciprocal, and these reciprocals are not the same. So it is a 1 to 1. If one is in this one is in 0 1/2 and one isn't, they have different ranges. Anybody from 0 to 1/2 is mapped to 1/2 to 1. Anybody above 1/2 is mapped to 0 to 1/2. Okay? So it's a bijection. Okay? Okay, so 0 1 is the same cardinality as the non-negative reals. Okay, so there, to compare two sets that are uncountable, to say they're the same size, you have to build a bijection, an actual bijection. Okay, so there is no infinite set whose cardinalities between, this is the generalized continuous hypothesis. So the power set of a set, the set of all subsets, is larger than the set. We showed that. Okay, we proved that. Okay? So, yeah, can you resolve this? What's the resolution of this hypothesis? Just since I mentioned it, they said you can't use math if math doesn't contain a contradiction, whatever that means. Okay? So what does containing a contradiction mean? Look at this statement. So this statement is a lie. Okay? Is this statement true or is it false? Well, if it's true, the statement is a lie, would say the statement is a lie, let's say it's true. If it's true, then this statement is a lie would have to be true, which means that this statement is a lie. Oh. If you say this statement is false, then that would say this statement is a lie. The negation of that is this statement is true. So true implies false, and false implies true. So there's a problem here. Okay? And here's another one. The barber shaves every person who does not shave themselves. Right? The barber shaves every person who does not shave themselves. Who shaves the barber? Who shaves the barber? Well, the barber shaves himself. Oh, that doesn't work, right? The barber doesn't shave himself. Oh, he would have to shave himself. Right? It's gender neutral. Themselves. Right. But yeah. Okay, so but you see the problem, right? You see these statements. When you're making statements in math, you're making statements, right? And then some of the statements they may not make sense at a certain point. Like that's what it means, these things. I mean, the English language here contains a contradiction, right? You see, that's what we're saying. So when you write down a mathematical system of proof, basically they either have to contain a contradiction or they're statements you can't prove. And this one actually said the continuum hypothesis is one of those statements. And the issue here is self-reference. It's this whole California problem, because it's all about me, right? It's when you start discussing the statement itself inside the statement, there's a problem. Okay? Now, there's another kind of thing that we do in computer science, and it's deeply, deeply in computer science. Like this, you can ignore this whole math stuff if you want, but can a program refer to a program? Can a program refer to itself? Right? I mean, there's this, did you do an interpreter that would interpret itself? This metacircular interpreter? Right? So the program was like running on the program, right, for the interpreter. Does that make sense? Okay. Uh-oh. This is a problem, right? These statements are a problem. They're self-referential in a way where it causes some issues, right? Because, they're powerful. It's a powerful language, English, right? But it can make statements like this. This says something, but the statement itself has no meaning. Okay, so this is the get around the paradox. Yeah, I guess you can get around the who shaves the barber, right? Here's another example. So this puzzle of building math was sort of built around this particular statement here. Okay, so this set theory they were trying to build in the early part of the 20th century was trying to write down a mathematical system where you could prove everything, prove all the statements, or disprove all the statements that you could write down in that system, and not prove anything that's false. Okay. So one thing is they said, okay, this seems pretty harmless. This is how you define a set. So there is some y, which is a set here, where for all x is contained in y whenever x obeys a certain property. Okay? This is not so bad. It's a little bit hard to parse, but it just says y is the set that contains all of the x's that obey this property, p of x. Seems pretty harmless, right? Seems like a reasonably natural thing to be able to write down in math. Y is simply the set that contains all of the x's that obey this property, that have this property. Right? That's what it says, to satisfy this proposition. Okay, let's make the proposition that x is not equal to x. Okay, now I'm just doing a syntactic substitution here. And I said there exists a y that satisfies statement 1 for P. Now, I want to say it should be definable. Like I wrote down a property, I used this thing. What it says is let's take x equals y. Okay. Okay, y is in y if and only if y is not equal to y. So that's what we're saying. So not an element of y. So that's a problem, right? If you just like plug in sort of a reasonable thing, all of a sudden you get this weird thing. Y is in y if and only y is not equal to y. So this is a problem, right? Because it's always weird. What type of object is a set that contains sets? But that's perfectly fine. You can have power sets. We've talked about power sets. And in fact, what they did when they saw this thing is they wrote this book and they started talking about type 1 sets and type 2 and type 3 and all the way up. And, 1,000-page book by Russell, and it would always fail. Whatever they did failed. Okay? And they would change the axioms. They try to come up with new math, and it just didn't work. Okay? So what it came down to is then no matter which axioms you write down, it's either inconsistent, you can either prove false statements, or it's incomplete. True statements can't be proven. Now we choose to do the second one. We don't want to prove false statements. So we have statements that we can't prove in our mathematics. Okay? So here's a concrete example. This is an example. There's no cardinality between the reals and naturals. In our current system, the math, the axioms that we use, you can't prove or disprove this statement. Okay? Yeah, it's not disapprovable in ZFC. It's not provable. This Cohen got a Fields Medal for this. It's hard to think about, right? All of this is hard to think about, right? Yeah, it's really the Cantor who did this diagonalization for integers. He's the one who defined this notion of countability. Yeah, he went crazy. He had some issues. Okay, so Gödel. Yeah, okay. So be careful, right? He was fine, but yeah, okay. So there's this great book it's a graphic novel by Papadimitriou. It's amazing, And so you should look it up. It's beautiful and amazing, and they talk about this story. Okay? Okay, so now I just want to preview what we're going to do next time. Is we're going to talk about whether we can write programs that actually do check other programs, right? This is the thing we're going to do. We're going to say that this whole theory is not just theory. It's fundamental to what we do as computer scientists. Okay? We're going to show you that we're going to fail at much of what we do. So we'll see that on Thursday. So I'll see you.
The discussion, I think like the original plan was to cover both countability and computability in this lecture.
Oh no, so the discussion has computability.
Discussion, yeah.
I should have gone faster, yeah, sorry, I could have.
Yeah, okay.